Hello everyone, welcome to our YouTube channel High Speed Board Design. Today we are going to discuss about the design guidelines for the PCB designing. In today's lecture, we are going to discuss about the most important design aspects that need to be taken care by the PCB design engineer. Whenever a PCB design engineer is designing the layout, in that case, how the layout is being imported. So the layout is imported from a schematic. So there is the schematic. So there will be the output file of the schematic which will be imported to your layout design tool. For example, let me take a good example of it. So schematic is usually designed in tools like Expedition, Orchid Capture is there, Orchid Capture or Design Entry HDL. So once the PCB design engineer gets these files, so the schematic usually contains all the logics. So whatever the logics are there in the printed circuit board or which are supposed to be there in the printed circuit board, all the design related informations will be there in the schematic. Now the job of PCB design and engineer is to convert this schematic into a layout. Layout is nothing but the three-dimensional representation of the printed circuit board, where it includes the placement. After placing or the components on the board, they need to do the routing. They need to check the stack up. So the part that we are going to discuss in today's lecture, this is going to help a PCB design engineer while routing and placement of the components as well as the vias. So first of all, as I have already created a video on stack up analysis and how a stack up has been created, you can always see the video in my playlist. Now let us move on to the next slide. So whenever a PCB design engineer lays down the traces, so that there are always bending in the traces whenever they travel from a transmitter to a receiver. So if a signal is traveling from transmitter to a receiver through traces, for example, this is my PCB board and here is my TX and here is my RX. So the signal is not going to travel like this, like in a straight line. So whenever the signal is traveling through traces, it always takes bends. So currently we are going to discuss about these bends in this particular slide. So whenever you're designing a very high speed board, in that case, these bends also create some kind of impedance loss. So today we are going to discuss about these kind of impedance losses. So whenever you are designing, being a PCB design and engineer, whenever you are designing traces, whenever you are putting up bends in the traces, you have to keep this thing in mind, whether the signal is a high speed signal or a low speed signal. If it is a low speed signal, then routing with a 90-degree will not affect much. But whenever it's a high speed signal, in that case, you have to be very careful while you are laying down all your traces or while you're routing all your traces on the PCB board. Let me quickly give you the example. So if you can see, there are three images which are available, A, B, and C. In image A, you're noticing one thing, the trace width is W and it is being routed with 90-degree angle. So as you can see, there is a 90-degree angle and 90-degree bend in my trace. So for example, if it is a high speed signal, this area, this white area which I have just now highlighted, it will definitely increase the capacitance as well as inductance of the signal. So as you can see, the capacitance effect will be much more higher than the inductive effect. So in that case, if we go to the basics where we have the formula of impedance, which is underscore L by C. So if the value of L goes high, so the impedance will definitely reduced, right? So in that case, whenever you are routing the traces at a very high speed, at that time you have to take care of it. So how we are going to chamfer this particular traces and what are the guidelines that we need to follow? So it's always advisable in image B and image C, I have already mentioned. So it should be 0.8 W to nearly 1.25 W. What does that mean? So the trace width if you take the M is the distance or the length of the chamfering, the length of the chamfering should be in the range between 0.8 of the trace width to 1.25 of the trace width. Okay, and the second part is the angle. So angle that is always being used is 45 degrees. So if you notice, this one is a 90-degree angle where you are seeing a decrease, a drop in the impedance. If you use this method, you're never going to see any impedance discontinuity here. So the signal is going to flow like this in the traces. So let me just brief it up again. So the guideline that we talk about here is, it shouldn't be 90-degree, it should be 45-degree. I'm talking about the high speed designs. I'm not talking about the low speed. In case of low speed, you can always use 90-degree, which will not much effect, which will not put much effect on your signal. 90 to 45-degree, and the chamfering length should be zero point 0.8 of the trace width to 1.25 of the trace width. So these are the guidelines that you are going to follow when you are putting up the chamfering part or the miltering part. So the second most important aspect that we need to see whenever we are routing the signals on the PCB tray is that whether we are routing the signals near the board boundaries, we call them as edges. Okay, board boundaries. So what does that mean? So for example, if you are having a PCB board and you're having a very complex design that has multiple components available, you need to route your trace near to the edges of the board. So what will happen if you route your trace near to the edges of the board? So will it affect on your impedance? Will it affect on your inductance, capacitance? So what are the effects that you are going to see? So in order to explain that, I have taken two examples here. One is A and one is B. So if you look closely, so there are two examples where in first example, so the trace is running 5 mils, just 5 mils from the boundary of the board. And another example, the trace width is moving 100 mils out of the board, inside the board, sorry. Okay. So in that case, I'm taking a signal with 65 ohm of trace impedance. So the trace impedance for both the traces is 65 ohms. If you see this one as well as this one. Now what effects will happen when we route the trace near to the board boundaries? First is there will be an increase in the inductance. There will be an increase in the inductance. Number two, the capacitance of the signal will reduce. Number three, if the capacitance is reducing, and by the formula Z naught equal to underscore L by C, so you will notice L is increasing, C is decreasing. So in that case, Z naught is directly proportional to N and Z naught is inversely proportional to capacitance. So the Z naught will definitely go higher. So you will notice in this example, L is 12.31 and in with 100 mils it is 11.23. And the capacitance has gone down from 2.68 picofarad per inch to 2.24. And you will notice the impedance, which was supposed to be 65 ohms, is now 74 ohms. Now what is the major reason behind it? So there will be electrical and magnetic field across this particular trace, correct? Some part of the magnetic field comes out of the board, which is being wasted. So the value of capacitance goes down and the value of inductance comes up. So the guideline that you are going to follow with this part is you have to make sure that the trace whichever you are routing should have at least 100 mils of distance from the board boundaries. So in PCB designing, there is something called root keep out. So the main purpose of root keep out is to keep the traces away and to keep them away from the boundaries also. Case of high speed board design, we never tend to put our high speed traces near to the board at all, because impedance is something which need to be maintained at very high priority in case of high speed board designs. So this the guideline explains you that you need to put your high speed traces inside the board and should not be near to the edges of the board. Now the next part is usage of serpentine traces. So first of all, let me explain about what are serpentine traces and why we use serpentine traces. So there are two factors that are involved. One is the length matching, and second is the timing matching, or you can call it as delay matching. So for example, if you are having a TX here and your RX here somewhere in the board, and your TX pin is here going to this particular part, and your other pin is on the other end of the part, so there is this length matching that need to be taken care, and there will be some delay that we need to introduce in this particular trace so that the length of both the traces are matched. First point. And the second is, so the time taken for the signal from transmitter to the receiver should be equal. So this will definitely increase your chances of getting high voltage. Like there are ramped voltage. You might have seen in few examples where you're getting some ramping over there in the signal. As I have explained it here in exhibit A and B. So if you notice, this is the B is what we are supposed to get the voltage with respect to time, but what we are getting this 1 TPD, 2 TPD, 3 TPD, and it got added to 5 TPD, which is 5 times of that, right? So let me explain what are serpentine traces. So in order to achieve the length matching and timing matching, we uses these serpentine traces which are being added to one of the signals in order to achieve these. Now, what are the guidelines that need to be followed while putting up the serpentine traces? So the first guideline that every PCB engineer should be aware of is, first, it's always advised to use long serpentine traces, long and fewer. So let me give you an example. So this is an example where I'm having 1, 2, 3, 4, 5 serpentine traces. Okay. And this is an example where I'm having total 3 serpentine traces. So it's always advised to keep a longer but a fewer serpentine traces. Now let me explain you what will happen with these serpentine traces, what these serpentine traces does. Everything comes up with an advantage as well as some disadvantages also. So if you see, the advantage of serpentine traces is length matching and timing matching. So the timing constants and the length constants are already matched. Now, what effect it will put on as an advantage for the board? So the most common disadvantage that it creates is this. If you can see here, so we are going to see the ramp voltage whenever your signal is changing its state from 0 to 1, level 0 to level 1. At that time, instead of going instantaneously in one way, it is going to take several steps and then it is going to come up to the V out level. How we are going to do this? So what are the guidelines? So the first guideline is use long serpentine traces. Okay. Second is the edges of the serpentine traces should be kept in such a way so that, as I already mentioned about it, right? Miltering of the tray and chamfering. So the chamfering should be done properly for these traces. So the second point is chamfering should be done properly. Chamfering should be done properly. And the third and most important part is usage of guard traces. Guard traces. So what are guard traces? So for example, if this is my signal traveling from transmitter to receiver using 5 serpentine traces. What am I going to do is I'm going to introduce a ground layer of guard traces over here. As you can see in this example, I've added ground traces over here. So what will ground trace do? So the ground traces will help the signal to reduce the impedance, whatever the impedance which I am getting, whatever the discontinuous that I am getting, it is going to reduce that. And instead of getting a ramped voltage over here, we are going to see this kind of voltage. So this is all about the serpentine traces. So the three major guidelines that we are going to follow in this one is it is always advised to use long serpentine traces, but fewer one. Instead of 5, it is always advised to use 3 or 2, whatever it is. Second is the champering. The champering at the edges of the signal should be should be done properly. If it is a high speed trace, then it is very important. Then the third is usage of guard traces. So whenever you use the guard traces, at that time you have to be very careful, because the voltage whichever we are getting in the form of a ramped voltage, we are going to get it instantaneously from 0 to 1. So the last and most important part is the via artwork. So what is via? Via are the cylindrical vertical traces that are being created in order to travel the particular signal from one layer to the other layer. For example, if you can see my stack up at the top, so this is L1 and this is L7, for example. So my signal is traveling from L1 to L7 with the use of a via. So now let me explain you or give you a brief introduction about the via. So if you can notice on the diagram, which is A diagram on the left, so this is known as the trace, and the metallic barrel that usually goes is known as, so these are the pads. So what are pads? So if you see the top view of it, it looks like this. On the PCB, it looks like this. So this particular part where the metal is there, this is known as pad. And this whole area where there is no metal added and it is an empty space, this is known as anti-pad. As you can see here, this hollow space is there, right? This is known as anti-pad, and this is the plane. So at particular layer, for example, here in my example at layer 5, I had a power plane which is already there. So this is how the plane has been depicted. This is the cylindrical tube which I can see here is known as the barrel, and trace from here it is going to somewhere on different layer. Okay, so this is how a VL looks like. Now what are the aspects that affect the VIA artwork? So how a VIA need to be designed? So that is one of the most important part. In order to reduce the crosstalk and reflections, we have to design our VIA very carefully. So what are the factors? So the basic factor, whenever we talk about a transmission line, we are going to look into the L, C, R, L, G, C, as you can see. So R and G, we don't put much of the effects on R and G, because the value of R and G changes very infinitesimally, like very small change will be there. But the value of L and C is something that need to be taken care, and that can be amended by taking few of the design guidelines, like following a few of the design guidelines. So in this case, I have, so if you can see the diagram on the right, which is exhibit B, you will see there is one capacitance, there is the parasitic capacitance which is being connected with even from the pad, from the barrel, between the plane. So this is the plane. So there will be a capacitance between the plane and the pad, between the barrel, even at the except the antipad area, as well as the between the plane. So how we are going to model that? So in order to do that, we'll go directly to the basics. So the value of capacitance is epsilon E by D, where A is the area of a parallel plate capacitor and D is the distance between the plate, right? So if you notice this, let me just erase everything. So we need to go to the basics. C is equal to epsilon A by D, where A is the area of the parallel plate capacitor, area, and D is the distance between the plate capacitor, like distance between the two parallel plates. Okay. Now just imagine this as a parallel plate capacitor. This one. So this particular area is acting as a parallel plate capacitor. This area is acting as a parallel plate capacitor. This area is also acting as a parallel plate capacitor. All these area act as a parallel plate capacitor. Now it will be very easier for you to understand. So C value I have already known, and Z naught is underscore L by C. So that means if the capacitance increases, my impedance will go down. So in order to adjust the impedance, we have to play around with the pad, with the plane, and the anti-pad area. Okay, so for example, if you increase the area of this plane, so area A increases whenever the thickness, when you increase the thickness, right? So the area of the plane increases, the trace thickness and plane thickness. So area of the plane increases. At that time, the Z naught goes down. And when we talk about, so for example, I have taken the anti-pad at very high value. For example, earlier it was a 5 mil anti-pad. Now I have increased it to 10 mil anti-pad. So now what will happen in this case? The distance between the parallel plate has gone higher. So the distance goes higher, the capacitance goes down, and resulting in impedance will go up. So this is how you're going to play around with your capacitance if you want to increase or decrease your capacitance and see the result in the form of a impedance. This is how you're going to work on it. If you require a separate video on how a VI is designed with a 3D depict of it, or if you need it anything related to the tool, I'll create a separate video for you guys. Just mention that thing in the comment. So let us quickly revise the points that we have already seen. First of all, we are going to look into the milted corners. So milted corner can be used in the trace to remove the excess capacitance and inductance. As I earlier explained, so if you are having a 90-degree angle, so in order to reduce this, you have to make it 45 degrees, and the value should be zero point 0.8 of width length to 1.25 of the width. Okay, these are what the guidelines that you need to follow. So chamfering is important when signal is at high speed. As I earlier mentioned, like whenever there is a low speed signal, at that time you don't have to much bother about the chamfering or the filtering. This thing comes into picture whenever your signal is at very high frequency, and each and every part of the trace matters a lot, whether it's the trace width or the height of the trace or the angles bended or the serpentine angle, whatever it is. So all these factors will come into picture whenever you're designing a high speed board. The third part is routing traces near the board's edge change its electrical characteristics and can increase EMI. As I explained earlier, whenever you put your trace near to the board edges, at that time the inductance value goes up, the capacitance values comes down, and the resulting impedance will go up. So in case of a high speed signal, we never advise anyone to draw or to route their signals next to the board edges or anywhere near to the board edges, because that will definitely increase your impedance, and increased impedance will definitely bring more discontinuities to your signal. Okay. So the next part is crosstalk must be minimized when using serpentine traces to adjust timing. As I earlier explained in the serpentine traces slide, so in that slide I mentioned about how the serpentine traces are created. So between these serpentine traces, there will be next near end crosstalk. So the crosstalk need to be reduced. So whenever you have a very least crosstalk, the timing is being adjusted properly. So the next point is it is better to use few longer serpentine elements than many short ones. This is one of the guidelines that I have already mentioned. So instead of using multiple small serpentine traces, it's always advised to use fewer but longer ones. So if you see this example here, so in case of A, it is always advised to use A instead of B. So the VI and antipad sizes strongly determine the VI electrical characteristics. As I earlier mentioned, the capacitance epsilon A by D and Z naught is underscore L by C. Whenever your capacitance increases, your impedance goes down. And how capacitance increases? When you increase the area of the parallel plates, and if you decrease the distance of between the traces, or you increase this antipad, right? As I mentioned earlier, antipad act as a distance. Okay, so if you increase the antipad, your capacitance will definitely go down and your impedance will increase. So you have to work on your VIA artwork in such a way so that the traces and the impedance is matched throughout the traces, whether it's on layer 1 or layer 7 or in the barrel itself. So if it is 50 ohm here, it should be near to 50 and it should be 50 here. So whenever there will be a discontinuity in this 50 ohm, we are going to see the reflections as well as crosstalk in your signals. Now the last point is non-functional pad helps secure the VI in the stack up but is not visible in the artwork, can be removed in high speed nets. So what are non-functional pads? Non-functional pads, what happened? Sometimes the manufacturer, while creating the board stack up, at that time they create the non-functional pads. Non-functional pads, for example, if they are putting the vias, so they are going to put multiple vias, and there will be few at few layers, those vias are not touching or those vias are not functional. So there is something that need to be taken care. So whenever you are simulating it, these are not seen, actually these are not visible in the artwork. So you need to remove them at a very high speed net. Whenever there is a high speed net, you have to make sure there should be no non-functional pads, only the functional pad should be. So in this whole video we have explained you about what are the major guidelines that you need to take care whenever you are designing a PCB board. So I would like to thank you all for watching this video till the end. I would just ask you to please subscribe the channel, like, and if you have any doubt related to it, just comment down below. In my community post, I have already asked you if you have any topic to cover with respect to board design, high-speed board design, PCB, signal integrity, power integrity. Feel free to comment down there. I'll start creating the videos on your on demand. So if you want me to create videos on demand videos for you, then please subscribe to the channel and put down your comments below, and I'm going to create more videos for you. Thank you and have a nice day.